results. One of the, and I said this last class, or I've said this many times, that quantum mechanics is a lot of hard work at the beginning to lead to very, very simple results at the end. So what I've written on the board is kind of a recap of last class. The idea is we're looking at rotation, right? We're going to spin something around an axis, and we're going to ask the question, what do the wave functions of that motion look like, right? How do we, right? We're going to want to track rotation, just like if you had a spinning object, you want to measure the rotation of it, angular momentum. We want to do the same thing. It's one of the important, kind of the key motions of molecules. It turns out the key motion in a lot of things, more than just molecules, is very fundamental. We're going to see a lot of things spinning in this class. So it's useful to think about the physics of it a little bit because it's so fundamental, right? And the idea is that we're converting from linear motion along a line, to motion around a circle. And so we have to change our language a little bit. Instead of thinking about momentum, velocity, position, instead we're going to think about our point mass or our object rotating around an axis, right? And it's going to basically sample 360 degrees of angle, and we're curious about how fast it does that, right? What's the angular momentum of it, how fast it samples that, and what are the energies that are allowed? What angular momenta are allowed in the system? And you'll see that time and time again in this class, that we're going to ask questions that you ask in physics. But what we're going to learn is that, what we learn is that you can only spin things at certain momenta, that there are momenta in between that you can't access. Right? That's the whole point of quantum mechanics, is that we quantize our energy. Right? Things become integer multiples, right? We have harmonics, the idea of octaves. You have a note, and you have further harmonics or octaves of that note. Because they're waves, after all. Waves and particles. So I put some physics on the board, and I'll just go through it again. The idea that the angular momentum is the momentum of an object being spun times the distance from the axis that you're spinning it around, which I call r. What we actually looked at is diatomic molecules. So the idea is that you're spinning this molecule around its center of mass. And you can show that this problem is equivalent to the idea of putting a point mass, at a position away from the axis, which is the bond length in this case, and think about this point mass rotating around the origin. Okay, it's the same problem. The idea is that we convert this object into a single object, which we represent by its reduced mass. If you remember, orbits are two-body systems in intro physics. You've probably done this math before. You have two objects that are separated by a distance. You can replace the physics of that with one object rotating around a center point. It's the equivalent physics. By doing that, you have to scale the mass by the reduced mass, which is the product of the masses of the atoms divided by the sum of the masses. And your moment of inertia, right, the rotational mass of the object, remember that we wrote, I didn't write it here, that angular momentum is the moment of inertia I times the frequency that it rotates around the circle, the angular frequency. Right, this is mass times velocity, if you will, in linear case. It's no different than P equals m times v. Same concept, except it's around a circle instead of on a line. And so when you do this math, you end up getting that the moment of inertia for this really easy. It's the reduced mass times r squared. All right, we'll see that again multiple times in this class. Diatomic is like this. So the angular momentum of the system is proportional to basically the mass times the distance between the two atoms. Reduced mass times the distance, right? And so when you do this math, right, we can come up with a Hamiltonian, which is L squared over 2I. It's the magnitude squared of the angular momentum divided by 2I. Just like for normal kinetic energy, for linear motion, it's P squared over 2M. Exact same thing, changing momentum to angular momentum and mass to angular mass, if you will, for moment of inertia. Same concept. But we have to do it in 3 dimensions, right? We had to define the spherical coordinate system, right, which was r, theta, and phi. Right? We define it like that instead, and we fix r. We make sure that r doesn't change, right? So the bond length is fixed between the atoms. We call that the rigid rotor approximation. R is fixed, so the molecule is completely rigid. And we end up getting a really complicated differential equation. When we plug our Hamiltonian, we get that really nasty differential equation that's got derivatives with respect to the angles and the radius, really nasty. But luckily it's been solved before. And what you get from it are the wave functions, which we call the spherical harmonics. They have this label y, that's what they're called traditionally. They're just a set of functions that take two numbers in, they have two indices. And out, when you plug in two numbers, you get a unique function associated with it. And these harmonics are like spherical waves. That's all they are. If you think of a sine wave as a wave on a line, the spherical harmonics are sine waves on a circle. Okay? They have very similar structures.
Professor,
yes?
Is the symbol for phi that you have on the graph the same? I mean, is there
yes.
symbols?
Yeah. I'm sorry. That's a very good question. So there's two ways I'll write phi in this class. One is because this is one way to write it, and another way to write it is this, they're the same symbol. Just depends on how lazy I am. So I'll try my best to write it like this, but if I write it like this, know that they're the same symbol. This is like the cursive version of this. That's all it is. They're just different fonts, if you will. And I'm not that consistent with it, so I'll do my best. Typically we think of theta as a circle of a horizontal line, and theta, or phi, as a circle with a vertical line. So you can kind of think of this as a vertical line through it. So that's the best I can do. I'll do my best to be consistent. But anyway, so you get these spherical harmonics. You can look them up there on Wikipedia. They're just a set of functions, special functions. They're sines and cosines, and right, they're just oscillatory functions defined on a circle, just like sines and cosines. And the beautiful thing about this is that the energies we get out of the Hamiltonian, the number that comes out of the Schrodinger equation, is this beautifully simple formula. Right? We have this term h squared over 2i. This has units of energy times some product of integers. Right? These are our quantum numbers. And we call, and as I'll explain in a second, these quantum numbers are associated with the length, the magnitude of the angular momentum. So as J goes up, that means we're putting more angular momentum into the system, which means we're spinning it faster. Right? So just remember, when L increases, that means, right, if L is getting bigger, I is fixed, that means omega is getting bigger. So the more L you have, or the higher your J quantum number is, the faster you're spinning your molecule. Okay? And so what this tells us is that you can only spin molecules at specific frequencies. Right? So let's look at that. I am going to write, let me make sure I have my units correct before I screw it up. We're going to rewrite a constant just to make it easier. We're going to call h bar squared over 2i. This has units of joules. Right? And we're going to rewrite it, define the constant b, right, you're going to see b a lot, as h bar h over, just regular h over 8 pi squared I. And what you get now is that the energy of a rotational state is 2bj, no, there's b j plus 1. The units of these, the unit of this, I've changed the units slightly. So I've renamed it, and I've changed the units into frequency. So the units of this are per second, which is frequency. Right, we also call this hertz, so seconds minus 1. Which is the same as hertz. That's the SI unit for per time, hertz. And so it's a frequency. It's basically the speed at which the molecule completes one full rotation of the circle. Okay? This is how fast that is. And so what it says is that the energy is a function of a number, J, just an integer, 0, 1, 2, 3, 4, 5, times this constant, B. And if we look at B, if we look at the structure of B, it's got a couple constants in it, pi squared and h, so it only depends on I. So let's think about how the energy levels change as a function of the molecule's moment of inertia changing as it's getting bigger or smaller. before we do that, let's think about what the energy difference between two levels are. So first what I'll do is I'll do an energy scale. So we'll write our levels, right? Each level can be notated by a J, J0, J1, J2, right? This is the ground state, or the fundamental mode. This is the first excited state, and so on and so forth. Right? Just like in the particle in a box, but except we're rotating this now. And so let's think about what the energies are. So if J is 0, this is all 0 overall, so energy here is 0. Here, let's put J equals 1. That's 1 times 2. This is 2B, at 2B of energy, or frequency, however you want to think about it. Our energy and frequency are equivalent to each other. Well, they're proportional to each other. J equals 2 is 2 times 3. That's 6B, and so on and so forth. Okay, so B, which we call the rotational constant, is a parameter that is only determined by the size and shape of the rotor. Right, because it's dependent on 1 over the moment of inertia. So as the moment of inertia gets bigger, right, let's go back again. The moment of inertia diatomic is its mass times the bond length squared. So let's make the bond longer, or for instance, make the masses heavier. Let's go from HCl to HBr, HI, right, make a bigger halide. That means that I gets bigger. So let me just write that here. So as molecule size increases, I increases, and B decreases. So what does that mean? Well, that means as the molecule gets bigger, the energy level spacings between individual rotational states gets smaller. Right? Just like in the particle in the box. The particle in the box energy spacing was dependent on the length, 1 over the length squared. So as the box got longer, the spacing between the energy levels gets smaller. And it's the same concept here. You can imagine if we make this system macroscopic, like we make our object, our diatomic this big, like this is a 1-to-1 scale object of it, right? Where your distance is on the order of a meter, and your mass is on the order of a kilogram, right? These spacings are tiny, right? So in fact, you can think of for a macroscopic rotor, the energy level spacing for a big molecule, macroscopic system, at the same energy scale as this, again, J equals 0 is at the same place, but all of them just kind of line up each other like this, right? You just get a continuum of states. Okay, so it's when you get to, that's not a very good drawing, but you get the picture. That's why this is important. That's why this is the idea that quantum mechanics at the small limit causes these discrete energy levels with big gaps in the between. And as the system grows to macroscopic scale, you get to something that when you start to blur your eyes, right, once the spacing gets small, you can just say that it looks like a square of states, right? You can be anywhere in this energy region. You can be anywhere, right? And this is what classical physics are, right? Because you can spin a macroscopic object of any angular minimum you want, right? And that just means that there's a continuum of states. You can put it at any angular minimum in between here. So the really nice thing about this is that we can determine B experimentally. And let me show you how. So what we can do is spectroscopy. Right? And spectroscopy is interested in differences in energy levels, energy splittings. So let's go ahead and calculate that. So let's calculate the energy between the Jth level and the J+1 level. And we have a nice easy formula for it. So the J+1 energy is going to be B J+1 times J+2. Right? Putting J+1 here, so it's J+2 and J+1. Minus B J J+1. Okay, and we have to do a little bit of foiling here. So let's go ahead and do that. Let's do B J J+1 J+2. That's going to be B times J squared plus J plus 2 minus bj squared plus j. Okay, just distribute out all the terms. So we have bj squared plus bj plus 2b minus 2bj squared plus bj. All right, so notice that the, I don't know where this 2 came from, sorry. Sorry, it's just bj squared, sorry. So notice that the j squared terms cancel. We have 2bj, this is now 2bj plus 2b. Factor out the b, the 2b, and we get 2bj plus 1. Okay? So, well, that's really nice, right? So that means now that the energy difference between two states is just a linear function of j, 2bj plus 1. So this, right, we can see that this is 4b, right, 2b to 6b, and this is 2b. Right? And so let's think about that. J plus 1, this is 2. 2 times, 0, we can do the lower state. So 0 plus 1 is 1, you get 2b. Then J1 to J2 is J is 1 here. 2b plus 2b plus 2, that's 4b, right? You can see that the energy differences line up, right? So we have these nicely spaced energy levels for rotation. And so if we go to our spectrum and say, okay, we'll calculate what B might be, all right, what the frequency is. We'll do it in just a second. But right, these are just energies or frequencies, right? So our wavelengths, right? So we can tune our spectrometer to this wavelength, and we should see a line at 2B, we should see a line at 4B, and one at 6B. Okay? And if we can find those lines, well, then we can use statistics and actually fit an experimental value for B. Because the spectrum is dependent on B. So let's do that.
Dr. Seifert,
Yes.
I just have a question.
Yes, go ahead.
We're coming down, we have bj squared plus bj plus 2b minus bj squared plus bj.
Yeah.
Wouldn't the last bj be minus?
Minus, thank you. So actually it's this. Sorry, there we go. That's better. 2bj plus b, and then factor out 2bj plus 1. There we go. Much better. Thank you. 2bj plus 1. Right. And not only this seems absurdly simple. And in fact it is, but this model, in fact, for diatomics is good to 1 part in 1,000. Okay? So it's actually very, very good prediction. It gets worse. As you start to spin the molecule up faster and faster, you have more centrifugal force that wants to stretch the bond, so it actually gets worse as J gets bigger. But at low J, it's actually 1 part in 1,000 or something like that, maybe even 1 part in 10,000. So it's a very, very accurate approximation. Bonds are fairly rigid. But let's just do a rough calculation. Let's just use this model and let's pick a real molecule pick a diatomic and see if we can, I'm going to write this, keep this up because we'll need it. Let's see if we can calculate some structure from this information. So what I'm going to use as an example, I think I used HCl as my example. Let me remind myself. Yeah, HCl. So what we're going to do is we're going to let this be Cl and this H. Okay? And what we're going to do is we're going to calculate the moment of inertia and then figure out where our spectrum is going to show up. Right? You can obviously do it the opposite way. You can detect the spectrum and then determine the structural parameters, but we'll do it the other way. So what we need to do is calculate the moment of inertia. So we need the masses and the bond length. So first we'll do the reduced mass. Right? And so that's going to be the mass of chlorine times the mass of hydrogen divided by the sum of the masses. And I'll ask you, what's the mass of hydrogen? Well, I wrote it down as 1 AMU, roughly. What's the mass of chlorine? Does anyone know?
35.
35. All right. We'll worry about units in a second. And then we have 1 AMU plus 35 AMU at the bottom. All right, remember AMU is just grams per mole. It's the same unit. We won't want to use per mole, but I'll come up with a conversion factor to convert this into atomic units or molecular units instead of molar units. And so when you calculate this out, it's the reduced mass of the system is 0.972 repeating AMU. Okay, so the rotation of this molecule is equivalent to sticking a mass at the end, right? You have imagine you have a point here that you fix to, and you've got a long rigid bar here that can rotate, and you stick a mass of 0.972 on it, and you set the distance of that bar to be the bond length of the molecule, and the physics are exactly the same. Right? So this is 0.97. This is basically equivalent of 0.972 AMU of masses. And R is whatever the bond length is, and I'll just write it out. So the experimental bond length for HCl is 1.275 angstroms. Right? So the equivalent physics problem is a mass of 972 AMU, 0.972, connected to the origin at a distance of 1.275 angstroms. Okay. And so now we can calculate the moment of inertia. We know the bond length and the mass. So I is going to be 0.972 AMU divided times 1.275 angstroms squared. And this is equal to 1.58 AMU dot angstrom squared. All right, well, these aren't very particular. These are useful units for us because we talk about bond lengths in terms of angstroms. Just a reminder, 1 angstrom, if you don't remember this, it's a good one to remember, is 10 to the minus 10 meters. It's a good unit because most bond lengths are on the order of 1 angstrom to 2 angstroms. And we do AMU, which is kind of a nebulous unit. So we want to convert this into, ultimately we want this in kilograms per meter squared. So we need to do a conversion, but I have an even better conversion, a really useful one. This is one that I've memorized. I've memorized just from using it so much. Is that, let me write it in big text here. We'll come back to this. It's that the moment of inertia written in AMU angstrom squared. Right, so if you have a moment of inertia of those units, it's the same as writing, you can calculate B by solving this equation. So B is we typically use for B the unit megahertz. That's just an atomic. Turns out most molecules, their rotational constants tend to be on the order of megahertz to gigahertz. And this conversion has a really nice number, 505,379. So in order to calculate B, we need to take 505,379 and divide it by our moment of inertia. And this ends up being 319.86 gigahertz. Or I'll just write it out in megahertz because that's the number you get when you do this in the calculators. 319.86 megahertz. Okay, this number's not that meaningful. I mean, because we don't often use megahertz to represent energy. Remember, these are energies. Right? This is an energy unit. Right? Frequency and energy are the same. So, in fact, typically we write this as, this is somewhere on the order of 11 wave numbers. Right? If you've done infrared spectroscopy in lab before, you've seen wave numbers before, it's about 11 wave numbers. So what does that mean? Well, that means then that when we go into our spectrum, we go take a spectrum, the first transition is going to be at 2 times that. So for HCl, we would expect to see this at 22 wave numbers, or 2 times 319, which is 640 roughly, 638 gigahertz. Right? So we have to shine kind of, we call that far infrared or millimeter wave, whichever way you want to look at it, right? And we should see a line here for HCl. And in fact, when you actually go and look experimentally, so what did we calculate B to be again? Right. Sorry, I have the next page. Yeah, so it's actually at 21.34. Sorry, no, I have it exactly here. 21.34 wave numbers. And where's the actual calculation for it? Did I not actually write it down? Okay, hold on a second. I'll get it for you. So let me put the screen down. Let's actually go look it up, because I don't remember it off the top of my head. But let me write it down. Theory says that it should be at 21.34 wave numbers. All right, so let's look at, right, all we've done is we've just calculated a bond length for it, put it in our masses and assume that it's rigid, and let's see how close we get. It lets me count. So I'm going to, once the website comes up, I'll show you the result. So in fact, these numbers are tabulated and have been studied for a long time. In fact, there are a number of databases of rotational transitions on the internet because, and I'll show you the one that I'm going to show here in particular called Splatolog, because radio astronomers need this information. Often radio astronomers look at stuff in this frequency region. Right, this is radio and microwave and millimeter wave, and that's where most radio telescopes work. And so you can imagine you're going to point your telescope at some cloud in space, and you see a bunch of lines, and you want to know what those lines are associated with, and this database has a database of all the really common ones. Of course, HCl is a fairly common molecule just about everywhere in the universe, so it's in here. So I'm going to go ahead and look up the frequencies for HCl. Right here, hydrochloric acid, and we did it in wave numbers, so let me set it to wave numbers. Or no, maybe I don't have wave numbers here, but we can calculate. And so here are all the different transitions of hydrochloric acid. These are all the ones that have been measured. But we want to look for the fundamental, which is the J1 to 0 transition. That's the ground state to the first excited state. And that is at, it's in megahertz, 625,901 megahertz. And I'll get it for you in megahertz in just a second. So we calculated it to be 319.86. So we 2 times that, 2 times 319.86 at 639.720 megahertz. Okay, so we're off a little bit. Right? So this is at 625, but we see it at 639. But that's not that big of a difference, right? That's, let's see, 639.72 minus 625.9. That's 13.82 divided by number 630, 620, 639, 72. That's right. That's 2.1% error. It's pretty good. It's pretty good. You really can't do much better than that. You really can't complain. The reason why it's off, in fact, has almost nothing to do with the theory that we chose. This kind of rigid model, this very simple model. It really is not. It's really not the source of this 2.1. But in fact, the problem with 2.1, and we'll talk about this when we get to spectroscopy a little more in molecules, is that this bond length is not well defined. And let me explain why that is. So this number is an average number. All right, I don't even know where it's measured from. In fact, I think maybe they even tell me what the bond length of it is in here. No, they don't. All right, this bond length, the question is, how do we assume what this bond length is? Is this an accurate measurement of the bond length? Is this actually what we see in experiment? And the fact of the matter is that the uncertainty on this measurement is probably somewhere on this digit right here. That the structure actually has some fluctuation to it because it's quantum mechanical. And let me explain what I mean by that. So if you've done homework 1, you've already kind of thought about this a little bit. So in 2.4 and 2.5, or 2.3 and 2.4, it asks you to calculate the root mean square deviation of position in the particle in the box All right, and what you should find, we define that the deviation, delta x, is equal to the average value of the position squared minus the square of the average position. And this is the same idea, the same equivalent, it's the physical equivalent of a standard deviation. Right? It's the same idea. Right? So it tells you a bit of, imagine you're making a measurement of the bond length or a distance, and you're going to get an average value. You're also going to get an uncertainty, right? There's some width to your error. Right? You always have some uncertainty to your measurement. So if I were to measure R, the bond length of the molecule, and make multiple measurements of it independently, and measure the counts, basically how many times I observed that bond length, so the probability, we're going to find an average value at 1.275 angstroms. But there's going to be some width associated with it. Right? Sometimes we're going to measure a bond length that's shorter than that, and sometimes we're going to measure a bond length wider than that. Because the molecule is just kind of oscillating, it's fluctuating like everything in quantum mechanics does. There's always some uncertainty. And the width of this distribution is delta x. Okay, and what you'll show is that for particle in a box, delta x is greater than 0. Right? So there's always going to be some error. This is not an instrumental error, it's not measurement error. Well, it sort of is measurement error, but it's not your fault. It's not because your experiment's not perfect, it's because, it's literally encoded into the physics. This is the entire point of uncertainty, is that every time you make a measurement of something in quantum mechanics, like a bond length, you ask the molecule what its bond length is, you're going to get different answers. You're going to get an average and you're going to get a standard deviation, but there's always some explicit error associated with that measurement. And you can't get rid of it. This is the best you can do. No matter if your instrument is perfect, perfectly precise, you're always going to have this uncertainty. Now, if that were the case, and the distribution of bond lengths for HCl look like this, and they're symmetric on both sides, right? There's an equal chance of seeing it slightly shorter than longer. Then the number that we're going to measure is this number on average, right? So that would be the number that the experiment would bring out, right? If there's an equal probability of the bond being shorter than it is longer than the average, then on average we're just going to see the average. But in fact, this is not what the distribution looks like for a molecule. And let me explain why. This is a little bit of an aside, and we'll see this more clearly when we get to molecules, but this is just a hint, is to think about what does that bond look like in terms of energy. What if I were to plot the distance between the atoms, and then I'm going to ask the molecule, what's your energy? All right, so I'm going to pull that molecule apart, and I'm going to put it back together, close it, and open it like that, and I'm going to ask how the energy changes. Now, we talked about this last semester. Right? We did the Lennard-Jones potential for two atoms that are attracted to each other in an ideal gas or non-ideal gas. We can use the same model for it. So the energy kind of looks like this. So as the atoms get closer and closer together, the energy skyrockets because the atoms want to repel each other, right? The nuclei are positively charged, the electrons are negatively charged. They look at each other, they want to move away. But eventually, as you start to pull the bond further and further apart, the energy, of course, increases because the bond wants to sit here at the average, at the equilibrium distance. But eventually, they get so far apart, the atoms don't talk to each other anymore, and the energy doesn't change anymore, right? This is dissociation, right? So this is, in some ways, this is HCl, and this is H and Cl separated, okay? And so this is just a potential energy, right? This is just potential energy of the bond. And so what we'll find, in fact, is that we can use this function, this model, to solve the Schrodinger equation for the bond. And so inside of this bond, inside of this potential, you get energy levels, like this, just like we do for rotation, right? Everything's quantized in quantum mechanics. We get these energy levels. These are what we call vibrations, vibrational levels. Right? We'll actually derive this later. Right? The idea is that we have an electron or a set of electrons being shared between two atoms, and we have a box that's shaped like this. Right? It's got a really high vertical wall on the close end and then kind of a shallow wall on the right end. Well, let's think about what the wave function or the average distance of the molecule looks like, or between the atoms looks like in a potential like this. Well, it's not going to be symmetric. Because let's imagine we're here at V equals 0, our ground state. Okay, our molecule's not vibrating technically. So let's think about how the molecule is biased towards one side of the system or another. Right? And so here's the average. If we'll say the average is right here, okay, in the middle. And so as the molecule starts to move to the left, as it starts to close together, it experiences a very sharp wall, a repulsive wall, right? So as the molecule starts to compress, there's a lot of energy making it want to expand again. Meanwhile, if you go to the other side, well, there's not as much of a repulsive wall there, right? It's much more gradual. So there's almost more of a bias to be long than short. The long distance behavior is less repulsive than short distance. So what that means is that then the molecule or the bond is rather going to prefer to be on the right side than the left side. Right? There's more impetus for it to be over here because it's not as repulsive. So in fact, what the distribution will look like is something like this. It grows up very sharply on the left side and then slowly decays to the right. Right? We still measure an average right here, but notice there's more chance of it being longer than shorter. So in fact, what happens is that what we actually measure is actually a weighted measurement, because the molecule on average is longer than you would expect by a symmetric potential. So the molecule tends to spend more time over here than over here. So what that means is that the observed bond length is longer than you would expect. Okay? There's more probability of seeing it at long distances than short distances. So let's think about that. So if that means if the experimental bond length is longer than you would expect, that means that the moment of inertia experimental is greater than the moment that you predict from theory, right? By just plugging in a number like we did. And that means that the B experiment is less than the B theory, the rotational constant, which means that the frequency that we measure experimentally is less than the theoretical number that we predict. So is that true? Well, experimentally we measure at 625 and theoretically we predict at 639. So in fact, that's exactly what happens. And that's all due to quantum mechanics. The fact that even bond lengths themselves are effectively uncertain parameters. That a molecule doesn't have a fixed bond length. It exhibits a distribution of bond lengths. And depending on the structure of that bond, it might be different than what you would expect naively. And you can see that borne out in the data. The data, we expect a higher frequency than what you predict, because the molecule in fact prefers to be slightly longer than what you would expect, just logically, from just a basic assumption. And you see this in everything. In general, molecules in their ground state, molecules that just float out in the ether by themselves, tend to exhibit slightly longer bond lengths when you observe them precisely than what you would predict from, say, calculations or NMR or something like that, because of this slight bias towards long distance. Right? So in general, for instance, we can go onto a computer and calculate the structure of HCl, get the bond length from it, and that bond length will always be shorter than the actual bond length from experiment, because when you calculate the structure of HCl, the way that you would do it with Professor Shao or any other computational chemist doesn't account for this bias. Right? You have to do some analysis to get this bias or the wave function. It just all the computer does is return the bond length at the minimum of the energy, right? And that's that number right here. This is the bond length of HCl at the bottom of the well. But the well's not symmetric. So the wave function tends to be biased towards the right side, towards long distance, and that makes the bond, the observed bond, shorter than you would expect from energy. All right, we'll see this again. But the take-home point is that this uncertainty has nothing to do with our predictions. Our theory isn't the problem here. The problem is that we've assumed that structure is rigid and well-defined. But in fact, it's not well-defined. It's a probability distribution. And the probability distribution, if it's not symmetric, then you're going to observe bias due to that. And that causes the structure to look different than what you would expect. Any questions about that? Okay. There are so many things in quantum mechanics, when you measure structure and get really precise about it, where you start to realize that you can't do any better because you're starting to compete with this uncertainty. Right? There's nothing I can do about this. There's no way I can make this any better. It's always going to be uncertain. There's always going to be some distribution, and I just have to accept that. Right? So there's always, what that means is that there's ultimately a theoretical limit to how precise we can really be about chemical structure. Right? We're always limited by the shape of the wave function. Of course, if we know exactly what the wave function looks like, then we know what the structure looks like. Right? We can calculate anything about it. But if we don't know what this wave function looks like, and we're only looking at what's the structure at the minimum energy, we're going to get the wrong answer. And so depending on what the shape of the potential looks like, tells you how bad the answer is. Because if the potential instead looked like this, so for instance, what if the potential is very sharp, like this? Well, then your average at the minimum looks a lot like the center of the wave function, because you have very sharp edges on both sides. So it doesn't want to go either way. It's supposed to sit in the middle. But if your potential looks like this, very shallow, and you draw your energy level there, well, it doesn't want to sit here. It wants to sit over here because the energy is much more shallow over there. So it's going to look like this. And so when you observe the average of the wave function, the average position, which is right there at the peak of your wave function of psi squared, it's very different than this value. There's a gap. Not only is there a gap, but there's a big uncertainty too, right? I only know my position as well as the mean and the deviation. Right? There's always going to be that error, uncertainty. Right? And because of that, really interesting things can happen in chemistry. Okay? Lots of really interesting reactions occur, and lots of really interesting structural things occur in molecules because of this fact that these wave functions, right, the actual structure of the molecule, which is defined by this wave function, is much broader and delocalized than you would expect. And it causes really interesting effects in structure. So in some ways structure is naturally undefined. We can only know it so well. Okay. So that was a little bit of a divergence from my topic of angular minimum. The only reason why I talk about this is because this is what my PhD work is in. This is what I've been studying since 2010, is doing this kind of work on rotation of molecules. The idea of measuring rotational constants B's. I've been measured hundreds of those in my life, and I've looked at systems like this. Systems that have structures that are very, very, very well defined. They have very rigid bonds, and they look exactly like you would expect. Very boring. And then there are some molecules that have very, very kind of floppy systems where the structure is very undefined. Right? There's an uncertainty to it. And they have different spectroscopic characteristics, and also they drive interesting reactions as well. So this is actually a universal property of molecules. All right, and we'll look at this math in more detail when we talk about vibrations. We'll talk about the difference of these and how they're borne out structurally and spectroscopically. Okay. All right, cool. Got 30 minutes. All right, so I want to change gears just a little bit. I wrote something on the board at the beginning of class about these spherical harmonics, right? Our wave functions for rotation rotational wave functions. Psi have two quantum numbers, j and m sub j, or just m, I call them m, and they are the spherical harmonics, and they're functions of the angles. Okay. And the thing that I noticed that we should notice is that the energy of a state associated with a j quantum number is just bjj plus 1. Right? So the energy is dependent on j, but it's not dependent on m. Right? So you need two quantum numbers, two numbers to define the wave function, but one number to define the energy. Right? And why is that? I want to talk about that because it's going to bring us into a very interesting topic that's critical for understanding the hydrogen atom and any angular minimum problem. Okay. We have to talk about where these quantum numbers come from. What do they measure? Okay. And the fact of the matter is that a quantum number is just a number. It's just a real number. Right? It's an integer, in fact. It's just an integer, right? This is 0, 1. This could be 0, 1, 2, 3, 4, 5, 6, so and so on. What is m, though? All right, so let's talk about the definition of these two numbers. The reason why I want to do this is because we're going to see these numbers in the hydrogen atom, and they're essential for understanding the structure of the hydrogen atom. Okay. So let's draw our vectors again. I'm just going to do it in terms of vectors because I think it's the easiest way to do things. Again, I always define my vertical axis as z. That's just by convention. And let me draw my x a little better. Yeah, that's good enough. X out of the board and y is in this direction. And then I'm going to draw my angular momentum vector of my system. Again, I can just treat my atom or my molecule as a point attached to a distance r, and it has an angular momentum L. All right, let's just say L is in this direction. And the important thing to note is that when we apply L squared to our wave function, we get h bar squared j plus 1. Right? That's where that energy comes from. Remember, the energy, the Hamiltonian, is L squared over 2I. The energy is bjj plus 1, so it's h bar squared. You get rid of the 2I out of it. So what this tells me actually is that the length of the L vector, the magnitude of it, is the square root of h squared jj plus 1. All right, so if L squared is this, then the length of the vector is the square root of that. So that's h bar square root jj plus 1. So the length of this is equal to, let me get rid of r because it's not the right, is h bar square root of jj plus 1. Okay, so as we start to rotate our molecule, we increase the j level, right? We increase it, go from j0 to j1 to j2. The angular momentum vector is getting longer. All that means is that we're spinning it faster, right? Remember that magnitude or length of L is proportional to angular frequency or speed. Right? So the longer L is, the faster the molecule is rotating. Right. So what that means is that as we increase the energy by j, increase j, then that means we're just spinning the molecule faster and faster and faster and faster. Okay. So when we measure the energy of our molecule, we're getting effectively the square of the length of that vector. But here's the problem. We don't actually know where that vector is pointing, right? Because I can get the same answer by drawing an equivalent vector in this direction, called L prime, right? Or I can draw one in this direction, double prime. We can draw it in this direction, right? And these all have the same length, but they're in completely different directions. Remember that when we rotate our molecule, so I'm going to rotate my molecule like this, in this direction, in this direction, that angular momentum is perpendicular to the axis of rotation. So as the molecule rotates on the board, the angular momentum is pointing out this way. So the direction tells you the orientation of the molecule. So if angular momentum is in this way, I'll let my marker be my diatomic. Angular momentum is in this direction. The molecule is rotating like this. On the green is the green, right? If the angular momentum is in this direction, it's rotating like this with respect to the axes. If it's pointing this way, it's rotating like this, right? And if it's pointing this way, it's rotating like this, right? So we don't know anything about the direction of it. So this is direction independent. Right? So when we measure the angular momentum by writing J, right, by measuring our line or our state, we know how fast it's rotating, but we don't know which orientation it is with respect to our system axis. Okay, so we need to be able to specify the direction. And so that's where the other quantum number comes from. What I'm going to do instead is I'm going to define the projection of L on Z. So the Z component of angular momentum, LZ, call that just a vector. All right, so let LZ be the Z component of L. Okay, so it's the direction with respect to L, or with respect to Z. Right, so maybe an easier way to write L is a vector of three components, Lx, Ly, and Lz. Right? So Lz is just the Z component. And what you can show is that when you promote Lz to an operator, and you ask the question, what's your momentum in the Z direction, you get, so I'll apply it to the wave function, you get m times h bar times psi. All right, so what m, this quantum number m that we have in the spherical harmonic, this other quantum number, is associated with the Z component of the angular momentum. Okay, so it tells you something about the direction. Okay, so let's think about that for a second. So again, what this says is that the length of the Z component is m times h bar. Right, so this length, I'll just erase this length, so the magnitude of Lz is mh bar. Okay? So depending on the size of m tells you how L is pointing with respect to the Z axis. So I can draw a nice figure of that. So let's just look along one axis. Let's just look along the Z x plane, for instance. And on here we're going to draw our angular momentum vector L. Okay? And then L can point in a number of different directions, right? It can point this way, it can point this way, this way, this way, this way, this way, right? And what are the allowed values? And it turns out that, and we'll talk more about this in the hydrogen atom, m can be any integer between minus j and j. Okay, so for instance, if j is 1, m can be minus 1, 0, or 1. I'll write that down. We'll just make a table. So if j is 0, the only allowed value is 0. J is 1, you can have minus 1, 0, 1. 2, you can have minus 2, minus 1, 0, 1, 2, and so on and so forth. Okay? So in general, there are 2j plus 1 m states, or m states. All right, so they're 0, 3, 5, and the next one's going to be 7, and so on. And they correspond to different orientations of L with respect to the Z-axis. So if I were to draw 2 h bar here, 1 h bar here. I have to erase this, sorry. So minus 1 h bar and minus 2 h bar. Right? And if we let j be 2, so that the length of L is going to be h bar times 2 times 3, the square root of 6. Right, so this is j equals 2. There can be 5 orientations of the vector. One is in, let me write it so that we can, let me draw it so that I have it nice and scaled. So one choice is something like this, but that's going to be, this is going to be j equals 2, m equals 2. Another one is going to be this one, j equals 1, m equals 1. Then there's the j equals 2, j equals 2, m equals 0. And then there's going to be the equivalent ones here as well, right? Okay, so what this means is that for every j so for j equals 2, there are 5 different orientations of the molecule. So what this tells me is that, again, the total angular minimum can only be quantized values, but also the orientation with respect to one of the axes is also quantized. So the molecule, when it's in j equals 2, can rotate like this with respect to the z-axis. Maybe it can rotate like this, right? That would be m equals 0, where it's perpendicular. Or maybe it orients like this and rotates like this, or like this, right? You can kind of imagine that. It's not easy to see. But you can imagine the molecule rotating like this, like that. Okay? And so there's only 5 orientations it can have. Okay, so for instance, that's really interesting because that means that not only can it have specific rotation speeds, right? Angular minimum, which is the length of the vector, it can only be oriented in specific orientations as well. Right, so the orientation, so the length, the magnitude of L is equal to h bar jj plus 1, where j is 0, 1, 2, blah, 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 and the direction with respect to the z-axis can only be h bar m, where m is equal to minus j plus 1, dot, 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 j minus 1 to j. There are 2 j plus 1 of these. Okay, so rotation of a quantum mechanical object is very restricted. It can only have specific angular momentum, but not only that, it can only have specific orientations. Right? There's only 3 possible orientations for j equals 1. There's only 5 possible orientations for j equals 2. All right, so it's very restricted. Right? And so what that means then is that each one of these M states is a unique orientation, so it has a unique wave function. Right? Each one of these is a unique rotational, right? It's possessing around the circle a slightly different way. Right? If it's pointing like this, or pointing like this, or pointing like this, it's processing around the circle, the orbit, the axis, the sphere that it rotates around in a slightly different way. So you need a different wave function for each state. So each wave function corresponds to a angular speed, a specific angular speed, and orientation, right? Which is why we need two numbers, right? We need to specify how fast it's moving, and we also need to specify in which direction is it rotating, right? So you need 2. Right, that's why those spherical harmonics have 2 numbers. But we haven't answered the question, why is the energy not dependent on the orientation? All right, why does it not matter? And there's a really easy way to figure this out. So imagine that, remember, these axes are completely arbitrary. Right? So what I can do, let's imagine, let me go ahead and redraw this. real quick, just as an illustration. Let's imagine I have two different M states. So maybe one in red is this one. Well, it's supposed to be red, but that's not red. So we'll call this the M equals plus 2. I don't know. And then we have the equivalent M equals minus 2, pointing the other way. Okay? Now, why do these have the same energy? Because all I need to do, in order to convert M equals minus 2 to M plus 2, all I need to do is just rotate my axis system. Right? If I rotate my axis system 90 degrees, then M equals minus 2 becomes M equals plus 2. Right? So the only difference between these two is literally I'm just taking the observer and rotating them like this. Right? I'm taking my camera and just rotating 90 degrees, and they're equivalent. So and this is just due to the fact that, right, the sphere is symmetric about any arbitrary rotation of the axis system, of its axes. Okay, so the way that I can interconvert between M equals minus 2 and M equals plus 2 is just rotate the sphere, or rotate my image of the sphere, the observer. The observer just has to change. And so even though there are two effective states, right, when I fix Z in this direction, Z can't move, I fix it, then there has to be 2. But there's also no difference between going positive Z and negative Z. Right? They're the same thing. Right? Remember, we take the squares of things. Ultimately, we take the squares, so there's no difference going negative or positive. So it doesn't matter. Right? So in fact, the M states are what we call degenerate. Right? They're the same energy. So in the presence, for a molecule existing in the vacuum, there is no orientational preference. Right? It can point in any direction. There are certain directions it can choose. It's a fixed number. There's 5 of them for j equals 2. So there are fixed number of orientations, because m is equal to minus j to j. But all orientations are equivalent. Okay? They're all equivalent. If the molecule is by itself floating in the air, there's nothing stopping me from erasing the z and writing an x here. Right? There's no difference. Right? Or it's just a label. Still the same amount of orientations, but they're all the same. Therefore, the energy of all the M states, the orientation states, are equivalent, identical. So in fact, if I were to draw the energy level structure for a rotational system, J equals 0 is one state, and then at 2b, there's actually 3 states overlapping each other, and then 5 states overlapping each other, and J equals 2. Right? And these are the M states. This is minus 1, 0, plus 1, minus 2, minus 1, 0, plus 1, plus 2. Right? I draw them separately, but they're not actually separate. They're all degenerate, same energy. Right? And I'll say these states, I'll use that word again. These states are, I'll use this word a lot, degenerate, which means same energy. It turns out if you start to think about the thermodynamics, imagine you have a mole of rotating molecules in your chamber or in your instrument. And you want to think about what fraction of the molecules are in J equals 1 or J equals 2, given the temperature. Right? You make a gas, right? Make a gas of HCl, heat it up to 300 Kelvin, and you need to ask the question, how many molecules are in a given state? And if you assume that each J state is just one state, right, that there's no M states, there's just the J's. There's one each level, one each energy. You get the wrong statistics. You get the wrong calculation completely. So in fact, if you, let's say for instance there are 12 molecules in J equals 1 and maybe 10 here and 15 here, let's just say, for instance, there are that many molecules. They're evenly split between these. There's 4 in the +1 state, 4 in the 0 state, 4 in the -1. So there's some moving like this, right? There's some moving like this, there's some moving like this, and then there's some moving like this, right? And they're equal and opposite. And so here there would be 2 in each. Right? They're all equally split between them. And so, but if you don't count for the fact that this degeneracy, that there are in fact 3 states of J equals 1 and 5 equals J equals 2, you get the wrong statistics. Right? These states exist. They're just all the same energy, and therefore any molecule in those rotational states just equally distribute amongst all of them. Okay? You get the wrong answer if you don't account for that. So that's why they exist. What we're going to see when we get to the hydrogen atom is that these M states, as we call them, are the p. This is the s orbital. This is an s orbital. These are p orbitals. These are d orbitals. Okay. So in fact, there are some situations where they will break energy, because, for instance, in an atom. Right. So let me write that down. So let's think about atoms really quick. Let's do carbon. So carbon's is 1s2, 2s2, 2p2. Right. So how do we draw the energy level structures? It's like this. 2s and then 2p. 1s, and we fill them up. And it fills up like this. And when we look at the wave functions for these, the wave function for this is the y00 state. J equals 0, no angular momentum, and 0 component. Here, this is going to be J equals 1 and 0. Is that right? No, sorry. It's still 0. Sorry, I apologize. Still 0. Is that right? No, sorry. Yeah, it's 0. And then this adds some angular momentum to it. And so this is going to be, so the P means there's 1 unit of angular momentum in the electron, and there's a -1, a 0, and a 1, +1. Right, so the p orbitals are just, each of the p orbitals, px, py, and pz, are just 3 spherical harmonics that are all the same energy. They're just slightly different orientations of how the electron orbits around, the orientation of the electron's angular momentum with respect to the axis of the atom. So again, if we think of the atom like this, here's the nucleus. We draw the z-axis in this direction. And here's our electron moving around the z-axis. And so this would be the +1. The electron moving around the axis this way. This would be the -1, or the 0. Sorry, this is M. And then this would be, so this is moving like that, and this is moving like this. -1. Right? And the wave functions associated with these motions in the p orbital are just the spherical harmonics. Just the spherical harmonics. All right, so we're going to see this structure of having subshells for a given angular momentum in the atom. It's explicitly encoded in the structure of the atom. Like the p orbitals are orbitals with 1 unit of angular momentum, where J is 1. The d orbitals are J equals 2. There are 5 p orbitals because there are 5 m states. The f orbitals are J equals 3. And there are 7 f orbitals because it's 2J plus 1. Right? And 2 times 3 plus 1 is 7. All right? That explains why there are 3 p orbitals, 1 s orbital, 5 p orbitals, and 7 f orbitals. Right? They're just spherical harmonics. Right? Everything. Right? This is the amazing thing about quantum mechanics that just blows my mind every time I teach this class or even think about it, is that I've talked about 2 very, very different concepts here. The concept of a diatomic molecule rotating, right? Just a big old object spinning around space, has the exact same physics of an electron orbiting this proton. You get the same kind of energy structure, an angular momentum structure, right? They're equivalent, effectively. The only difference is that in the hydrogen atom, there's some attraction between the proton and the electron. Right? There's electrostatic attraction. And that changes things a little bit. The electrostatic attraction is what gives us the 1, the 2, and the 3, the ends. 1s, 2s, 3s, 4s. That attraction is what gives us that structure. But the SPD attraction, the SPD structure of the orbitals is exactly the same as the diatomic. It's the exact same behavior. Right? The same structure is seen in both systems. How much time do I got left? 5 minutes. All right, good. So that means on Monday we actually good time. So here I'm just going to set a problem up for us to think about for Monday. Is that what I've specified is I can say with certainty, I can tell you how much angular momentum the system has, right? That's J. I can tell you the orientation with respect to one of the axes, that's M. But remember, we're in 3 dimensions. Right? What about the direction in the xy plane? Right? I've only talked about it along the z-axis, but what about the direction in the xy plane? Right? Maybe it's not pointing along the board, but it's pointing out towards you guys, or pointing this way, or pointing that way, right? I haven't said anything about that, right? All I've said is that I can tell you the orientation along one axis and the length. But what about the other 2 coordinates? Well, it turns out, and we'll derive this explicitly on Monday, the most we can ever know is L squared and the projection along one and only one axis. So if we can define L sub z is defined explicitly, then Lx and Ly are completely undefined. We lose all information about x and y. So in fact, what I'll show is that in fact, the angular momentum vector is not a vector at all. But remember, we know nothing about the orientation with respect to the xy axis, right? This xy plane. It's kind of in and out of the board here. So what in fact, it's not really a vector that we're measuring, but rather it's a cone. Let me see if I can draw this. Right, if you draw a cone around the z-axis, I'll try to draw a better picture next time. The vector, the angular momentum vector, can be anywhere along that cone. Let me see if I can do it a little better. So here's my z-axis, right? And so here's my angular momentum vector with my molecule, right? And so I set it to some z component. All right, so let's just say it's like that, right? This is all I can know. But in fact, the angular momentum component, if I sweep a circle around the z-axis is the center of the circle, the angular momentum can be anywhere in that circle, right? I know nothing about that. It's completely undefined. So in fact, the molecule can be in any orientation with respect to these axes, along the plane of the floor, if you will, right? So it actually shapes a cone. And that's all we can know. That's the only thing that's all we can say about the position of the orientation. We only can know 2 things. We can know the length, and we can know the projection along one axis. But we can't know the other 2. All right, and so at the beginning of class on Monday, I'm going to show you an experiment. We'll do it on the board. We'll think about it a little bit. It's a thought experiment, but one that you can do in lab that proves this. That if you know information about the z-axis, you lose all your information about x and y. Okay? This is once again is encoded. It's not a limitation of the theory. It is physical reality. Right? It's not because we don't have the map to describe it. It's that it's physically impossible to know these things. It's encoded in the universe. That all we can know about angular momentum for an object are 2 pieces of information, and the rest is undefined. And when we try to think about another one, like maybe we want to measure along x, we lose the z information as well. All right? So I'll show you guys that on Monday, which will allow us to talk about spin angular momentum, like for the electron, and that should get us in a good position to really tackle the hydrogen atom. Okay, guys, have a nice day. I'll see some of you in an hour or so. Have a nice day. I'll have problems set for you guys sometime early next week as well. Take care, Jacob. Thank you. Thank you.